Okay, welcome everyone to my continuation of what is geometric topology. Today I would like to tell you about, well, not complements basically, and never forget to complement, or a little bit more algebraic in nature, the associated knot group. So a group associated to a knot, and the group is an invariant of the knot. That's the whole point. As we have noticed by now, that's the whole point of knot theory. And in this case, it's not just a sequence of numbers or polynomial, but rather a whole group associated to a knot. Usually a quite complicated one, we'll see. But let's get started. So the idea is the following. So I have my knot sitting in R2, R3, or a little bit more precise, I would like to go to S3. The difference is not really huge. We can kind of ignore it. So the idea is the following. So if you have R and you want to go to S1, what you do is you just take the point at minus infinity, take the point at infinity, and identify them. So you just rev it up in a circle, and it's this kind of one-point compactification of R S1. And you can do the same for R squared and S2, which then will look a little bit like a spherical graphical projection. So here you can also think of going in the opposite way by just this is a really horrible picture, but just very graphically project from the north pole of S1 to R. You could think of the same in the two-dimensional case, and well, if you can imagine the next step. So here's this very graphical projection, again a very horrible picture. So from the north pole you can somewhat project somewhere, and that's a connection of S2 and R2, and something similar works for S3 and R3. So it's really still the same picture, but now we have this point at infinity, and if you think of a knot, then you can do some kind of lasso move now, right? So you can just pull the knot above your head if you want. So a knot is now sitting in S3. And the knot complement is the following. So remember that I told you that I only want to consider knots that I can thicken anyway. So I could think of my knot as this thickened picture here, just some thickened type of torus. And I just take it out, and whatever remains, strictly speaking, I take off the interior, but anyway, whatever remains is called the knot complement, and it's a three-dimensional space where, as you can see, so for example, the red lines here are in the knot complement, and what is not in the knot complement is everything in white, because that was the knot, and the knot is taken out. For an explicit example, these things are usually very complicated, but for an explicit example, if we take the unknot out of S3, so the unknot is pretty boring, then we can think of this as being a solid torus. And how do we see that? So it's, okay, so imagine the usual picture, the x-axis, z-axis, and y-axis. So I have no idea which one is which, but it doesn't matter anyway. So x, y, z. And, well, that's R3, not S3, but in R3 we can do the following. We can now think of our little picture here, the knot, as being just the z-axis, because in S3 kind of we have identified those 2 points, and it really just closes into a loop. And then the knot complement is just R3 without the z-axis, and yeah, so the z-axis is then the remaining hole in the solid torus. That's kind of the picture here. In general, as I said, those complements are rather complicated. So even for the unknot, that was not quite a completely trivial yoga, just taking out the z-axis, but they're really, really good invariants. So the knot complement is an invariant of the knot, a really strong one, actually. We'll write down a more explicit statement in a few slides. Okay, but whenever you have some complicated object, you would like to associate to it something simpler, like a number or polynomial, or in this case, a group. So what you do is you associate to it pi1, and that's called the knot group. If you don't know what pi1 is, I'm going to explain it roughly here, and then on the next slide I give you a completely algebraic description. So actually we don't really need to know what pi1 is, but if you know what pi1 is, the knot group is just pi1 of the knot complement. So here's again some pictures. So I have my knot here sitting somewhere. So here a little bit thinner, the blue line is still the knot, and we take it out. So this actually is the xk here. Everything except the blue line basically is xk, and the knot group is now just given as follows. You fix some point in xk, doesn't really matter which one, up to conjugation, so up to isomorphism, and you consider loops just in xk, and you consider those loops up to homotopy, whatever that means. So basically up to some deformation. And whatever kind of group you get, so that you get a group for the following reason. So if you start somewhere and you go around in a loop, Yeah, and you now end up at the same point, and you go around in another loop. Then you compose them. It's just the loop that goes, well, both loops, and then the other loop. That's a composition loop. So this actually has naturally the structure of a group, and that's what's called pi1. And in particular, this pi1 is generated by loops in the complement, right? So like this A or this B or kind of other type of loops things. And it's a really good invariant of the space. It's extremely hard to, well, it's extremely hard in general. In particular, we'll see an example on the next slide, but it's really good. So if pi1 is still a little mysterious to you, here comes the completely explicit description. It's called the Wirtinger presentation. And it works as follows. So this is isomorphic to what I just told you. So in some sense, we can forget about the geometric description. Okay, so this is how it works. The usual yoga, we have our knot projection here, and we label the arcs by some integers by some symbols, ABC, for example, and the knot group is then the group generated by ABC modulo relations around each crossing. So you have three types of relations around those crossings. Slight catch, I will explain the relations in a second. Slight catch, I need an orientation to determine the relations, but let's not worry about it too much anyway. So I said again, the generators are just the arcs, the segments in the projection, and the relations are given as follows. You just look locally whatever is going on. So here, if A is going over in this way and B and C, then your relation is AB, CA. So for example, here, the knot goes all the way like this. So here's the orientation, here's the orientation. In other words, this crossing here is actually this crossing with green going over. So B goes over and A and C go under. So this relation should then be, let's write it down, B, C equals AB. And yes, I got the relation as well here in the description. And then you just, for each crossing, you add a relation. So generators are given by the segments, relations are given by the crossings. You get a group given by generators and relations, and that's your knot group. Slight problem with this description. It's a very explicit description, but the problem is your group is just given by some generator and relation nonsense. So it's usually quite hard to identify the group more explicitly. Here in this case, it's rather simple. So you have three relations, and one of them, well, for example, you can use this one here to get rid of C, because C is, of course, then just B inverse AB. Yeah, so you can get rid of C, and if you get rid of C, you get an equivalent description, which looks like this. And that's the braid group B3, the braid group in 3 strands. So the point is, this is extremely, it's exactly this description, just explicitly in terms of generators and relations. It's very simple in terms of generators and relations. Just generators are the arcs, and relations are, well, given by 2 rules along the crossings. You just read it off. The problem is that usually you need to identify the group in a more explicit way, and that might be rather tricky. But it's really cool invariant. So the knot group is, what a surprise, not invariant. And well, the topological and the algebraic definition, they just agree that's a result of Wirtinger. And this is really kind of the point here, because the topological incarnation is the geometric construction, and it's kind of clear that it is a not invariant, but hard to compute, or it's unclear how to compute it actually. And for the algebraic invariant, it's exactly the opposite, and identifying them is exactly what you want to do. Right? One of them is easy to define, but hard or unclear is how to compute it. The other one is clearly computable, but it's somehow unclear why it is a not invariant, for example. But identifying them then kind of kills everything at once. So let's you kill one bird, well, 2 birds with 1 stone, not 1 bird with 2 stones. I guess 2 birds with 1 stone. And so this is a really good not invariant, and the complement is actually even better. So the complement, for example, tells knots apart up to mirror images. You still can't detect the mirror image. So 2 knots are the same up to mirrors, even only if their knot complements are the same. So the knot complement is really, really strong not invariant. It's just very hard to work with it in practice. Remember my example with the unknot. That was already not quite trivial, and we're talking about the unknot here. So the unknot should have a reasonably simple answer, right? So that's what you at least would expect. Okay, so I actually already told you what the next slide is because we still can't distinguish mirror images. They both get the same knot group. It's a braid group from before. So this is a simplified one. So BAB equals ABA. And we still have no chance to distinguish them, although we have, even not using the complement, but that's just a really, really strong invariant, but it still can't tell mirrors apart. So we still can't do anything here. So we need to dig a little bit deeper, but maybe in the next video, I guess in the next video, we'll see a solution to that problem. And we can actually distinguish left and right-handed trefoils. That's great. Okay, so wrap up. So the knot group or the knot complement is a topologically defined invariant. Just take your space, remove the knot, whatever remains is kind of what you want to study. And in order to study it kind of algebraically, you use the knot group, which is basically given by generators and relations using this verting representation, just one generator for each arc, for each segment, and one relation for each crossing. And that's a really good and strong knot invariant, and people really like to study it. Problem usually is that it is a little bit hard to work with. It's just some random generator and relation presentation, basically. So what you would like to do in the end, or what you need to do, is you find some nice representations and try to play around with those representations. But anyway, we still can't distinguish left and right-handed trefoil, which is very, very disappointing at this point. Anyway, I still hope you enjoyed the video, and I also hope to see you next time.